On September 26, 2022, a spacecraft the size of a vending machine, traveling at 14,000 miles per hour, crashed directly into an asteroid. On purpose. The asteroid's orbit changed, not by seconds, by 33 minutes, 3 times more than anyone predicted. And right now, a second spacecraft is approaching that asteroid to measure exactly what we did, because we need to understand it well enough to do it again. The asteroid is called Dimorphos. It is 160 meters across, roughly the size of a football stadium, and it orbits a larger asteroid called Didymos, which is 780 meters wide. The two of them form a binary system, tumbling together through the inner solar system. Neither Didymos nor Dimorphos is on a collision course with Earth. That's exactly why they were chosen. Planetary scientists needed a target that was safe to hit, close enough to observe the results, and small enough that even a modest spacecraft could make a measurable difference. What they didn't know, before September 26, 2022, was whether this would work at all. The idea behind planetary defense is straightforward. If you find an asteroid heading for Earth far enough in advance, years, preferably decades, you don't need to destroy it. You just need to nudge it. Change its speed by a fraction. Enough that when it arrives at Earth position, it arrives a little early or a little late and misses entirely. The question was never whether the physics made sense. The question was whether we could actually pull it off. The Double Asteroid Redirection Test, DART, was the attempt to find out. NASA built a spacecraft weighing 600 kilograms, aimed it at Dimorphos, and let physics do the rest. No explosives, no nuclear device. Pure kinetic energy, mass times velocity, directed at a specific point on a specific rock in space from 11 million kilometers away. At 7:14 in the evening, Eastern Time, DART hit Dimorphos at 6.1 kilometers per second. The impact was watched live by people all over the world. Telescopes on Earth, the James Webb Space Telescope, and the Hubble Space Telescope all observed simultaneously. The results came in over the following weeks. Before the impact, Dimorphos orbited Didymos every 11 hours and 55 minutes. After the impact, that orbit had shortened to 11 hours and 22 minutes, a change of 33 minutes. The prediction had been 10 minutes, maybe 12 if things went well. 33 minutes was not the expected result. It was 3 times better than expected. And the reason tells us something important about how kinetic impacts actually work in space. When DART hit Dimorphos, it didn't just transfer its own momentum into the asteroid. The impact blasted a plume of debris, rock, dust, and rubble, outward from the surface. That ejecta, flying away from Dimorphos at speed, acted as a second propulsion system. The more material ejected, the greater the total kick to the asteroid. In other words, the asteroid helped push itself. The impact was more efficient than a simple collision, because Dimorphos had enough surface material to amplify the effect. This is important. It means the success of a deflection mission depends not just on the impactor, but on the structure and composition of the target. A solid iron asteroid responds very differently to a loose rubble pile. Dimorphos, it turns out, is the latter, a loosely bound collection of rock and regolith that came apart dramatically on impact. But here is what we still don't know. We know the orbital change. We don't know exactly why. We don't know the precise mass of Dimorphos. We don't know the density of its interior. We don't know the exact size or shape of the crater DART left behind. We don't know how much material was ejected, or in which direction, or how that ejecta redistributed itself around the Didymos system. Without that data, DART is a successful experiment with an incomplete result. We know it worked. We don't know how well or why in enough detail to confidently plan the next one. That is why ESA launched Hera. Hera is a European Space Agency spacecraft that launched in October 2024 and is currently on final approach to the Didymos system. It will arrive in November 2026, a month ahead of schedule. Where DART was a hammer, Hera is a forensic investigator. Its instruments will map the surface of Dimorphos in detail, measure the mass of both asteroids, scan the interior structure of Dimorphos using radar, characterize the crater DART left behind, and determine the precise momentum transfer that occurred in September 2022. Hera will also deploy 2 CubeSats, small shoebox-sized satellites, to orbit Dimorphos at close range and gather data from angles the main spacecraft cannot reach. The data Hera returns will transform DART from a single successful test into a repeatable, calibrated technique. The difference matters. A technique you understand can be adapted. A technique you don't understand is a one-off. If we want planetary defense to be a reliable tool for protecting Earth, we need to know the variables. Hera is how we learn them. There are currently more than 2,000 known potentially hazardous asteroids, objects large enough and with orbits close enough to Earth that a future impact cannot be ruled out. None of them are on confirmed collision courses, but none of them will remain in their current orbits forever. The window for deflection is long, but it is not infinite. The earlier a threat is detected, the smaller the nudge required. A spacecraft like DART, launched decades before an impact, can change an orbit with a relatively modest push. The same spacecraft launched 10 years before impact has a far harder job. 5 years is nearly impossible with current technology. DART proved the concept. Hera will prove we understand it. And what comes after Hera? A global network of monitoring telescopes, standing deflection protocols, international coordination, depends on whether the data Hera returns shows that we can do this reliably. We hit an asteroid. It worked better than expected. Now we need to know why, because the next one might not be a practice run.